So we get minus a e to the 2t equals to c1 e to the 2t. So therefore c1 is equal to, therefore a is equal to minus c1. And that will give me your solution, Luke. X of t is equal to c2 e to the 2t minus c1 t e to the 2t. So there's your scalar solutions. And if I rewrite those as a vector solution, it's interesting. If I rewrite those as a vector solution, this vector solution has the form C1 minus C1t e to the 2t plus C2 e to the 2t. And down here, what do we have? C1 e to the 2t. Did I do that right? So that looks like C1 e to the 2t times minus t and then a 1 plus C2 e to the 2t times 1, 0. So this is our beloved eigenvector solution. This is something mysterious and different that we would like to find a more systematic way to find, because we don't really want to be forced to go through all this stuff whenever we have this kind of problem, right? Because this problem is nice. It doesn't have to be uncoupled. Uncoupled is nice. Generally, they're not uncoupled. They're all intertwingled. So first you have to untwingle them before you could get to the uncoupled thing, and then integrate, and then substitute, and then that's just no way to be. We need a better way. Anyway, that will happen in a future lecture. I just want to point out to you that there is a gap in the eigenvector method. I think I've shown that. Let me show you guys some stuff using the projector. It just won't trust you until you plug it in. It's like, you don't have anything to present. It appears no video source has been found. I don't believe you. Believe me now? Yeah, really. Anyway, I hope last class I showed you guys enough matrix algebra and stuff so you can do those problems. Is that fair? I mean, if you have questions about them, you can ask me while we're waiting for this to load up. Anything stand out? I think I mostly asked you like multiply matrices and add them, and just a few basic sort of tasks to try to get you thinking about how to manipulate matrices and calculate, right? So I hope nothing in there was too tricky. Certainly was not my intent. Now here's something I haven't talked about at all. This is the other way of solving systems, is by operator methods, which is basically to just sort of brute force eliminate variables. Not a fan of this method, so I'm going to go on. I mean, I might come back to it. I'll come back to it when it's time to come back to it, all right? There are problems which are good for that. All right, so I should have looked at my table of contents more intently before I did this to us. Oh, sorry. Come on. Eventually I will get to. All right, so just recap. That's normal form for second order, normal form for third order. Nothing terribly surprising there. If you take this second order differential equation, ay prime prime plus by prime plus cy, we can do reduction of order like I talked about last time, and check it out. It's this corresponding 2x2 system. Fun fact, the characteristic equation for this is exactly the a lambda squared plus b lambda plus c equal to 0 that you found before. Change notation, but the algebra stays with us. And so, you know, And then the same thing is true for this. If you look at the nth order problem, there's a corresponding system of n differential equations, and it has what's called the companion matrix. So this is the matrix that you get from doing reduction of order n-fold times on an nth order problem. You end up with this rather special kind of matrix, which has interesting connections into the larger theory of linear algebra and something called the rational canonical form. But anyway, I digress. I would like to show you an eigenvector problem that has not such ugly solutions. Anyway, reading these things would be good, but I don't want to talk about them here. Come on! Sorry, I should have taken 3 more seconds to look at my table of contents. I'm just trying to get to the eigenvector solution. Here we go. So we worked that out today. Here's one that's a little bit better. If I'd taken 2 minutes to look up this problem before I dove into this, we wouldn't have been subjected to the ugly square roots. But I guess it's good to do that. I just don't feel like so yet. All right. This matrix comes from this system, minus 4x minus 4y plus 5x plus 2y, right? And so the characteristic equation, minus 4 minus lambda, 2 minus lambda, do the determinant. That simplifies to lambda squared plus 2 lambda minus 3, which factors. Ah, beautiful. Now, I was telling you about a secret. There's a secret you should know. Beautiful secret. That the trace of a matrix is the sum of its eigenvalues. And the determinant of the matrix is the product of its eigenvalues. So for 2 by 2 matrix, like this, the trace of A here is 2 plus 2, which is 4. And the determinant, well, it's 4 also. Funny. Anyway, that's because the eigenvalues were 2 and 2. 2 plus 2 is 4, and 2 times 2 is also 4. Sorry, this is not a very great example for these formulas. The ugly one we had a second ago, which was what? What was it? What was the ugly one? I can't remember. 1, 2, 1, 3. So this has trace of 4, and it has determinant of 1. All right, 3 minus 2. And if you look at those, 2 plus root 3 times 2 minus root 3, that product gives you 4 minus 3, which is 1. So the product of the eigenvalues is 1. And the trace, if you add these two together, you get 2 plus 2. So you also get 4. So you can check your calculation for 2 by 2 systems pretty nicely with this, right? So the sum of the eigenvalues should be the trace of the matrix, which is what is the trace of the matrix? Sum of the diagonals, all right? Easy enough to remember. And the determinant of the matrix should be the product of the eigenvalues. So this is a nice check on your calculations before you get too far down the garden path calculating eigenvectors and so forth. Yep.
What do you mean by the sum of the diagonals? Like the sum of the numbers?
So like here, minus 4 plus 2 equals to minus 2. The trace of this is minus 2. As you can see, the eigenvalues are minus 3 and 1. Minus 3 plus 1, minus 2. Woohoo! It works. So here are the details for this one. Eigenvalue 1, eigenvalue minus 3. So to find the, so this one I'm going to find the eigenvector with eigenvalue 1, a minus I times u1, which gives me this. But if you look, it's pretty easy to see here the first equation and the second equation are the same stupid equation, right? I mean, it's obvious here. It's in your face. That's just minus, this is minus that one, right? So you pick whichever one you like, and I say v is equal to minus 5u. So that's a generic eigenvector. But of course, you can just factor out the u. I would probably put, I would set u equal to 1 if I'm just after the particular thing, right? Yeah, u equal to 1. So that gives me eigensolution e to the t times 1 minus 5. That's a transpose again. That makes it into a column vector. And then my eigenvector with eigenvalue minus 3, I have to solve this system, which ends up giving me v equals to minus u. So I get the eigenvector 1 minus 1 after I set u equal to 1. And so a linear combination of this and that is the general solution. All right. Like I wrote down here. So this is the general solution for that problem. You just take eigenvector solution plus eigenvector solution. There's your scalar solutions. There's your x. There's your y. And here, for the first time, for a specific example, is the fundamental solution matrix. E to the t. So this is like x1. This is x2, just written as a big old matrix. No c1s and c2s in the fundamental solution matrix. The fundamental solution matrix, by the way, is not unique for a given problem. There's lots of different ones. They're related in a very special and simple way, which we'll talk more about later. Any questions about this example? It takes me at least a half hour to work through one of these, so it's important for us to kind of like just scan through a few to just talk about them. This one is already uncoupled. See, Luke, if we used your method, we don't even need eigenvectors because this is just basically dx dt equals to minus 3x and dy dt equals to minus 3y. So you know how to solve that, just straight up. It's x equals c1 e to the minus 3t, y equals c2 e to the minus 3t, done, right? But it's also nice to notice that this is very, it gives us very peculiar algebra here because we get, the point of this example is that when you have a repeated eigenvalue, it doesn't necessarily mean that this happens to you either. Like it doesn't have to be that there aren't enough solutions. In this case, we have a repeated eigenvalue, but there are two solutions. The eigenvector solutions are enough here. Just the fact that the eigenvalue was repeated is not what killed the method. It was something else. It was something deeper, something more subtle in terms of linear algebra. That's a tease for later. Okay, so anyway, basically when you plug in eigenvalue 3, you get no equations. That means that everything is an eigenvector with eigenvalue minus 3 for this matrix. Because it's just minus 3 times the identity matrix. And the identity matrix times any vector gives you back the same vector again. If you put a minus 3 in front of it, well, then it gives you minus 3 times the vector again. Any vector. So, yeah, you got lots of choices. But there's a nice choice, 1, 0, and 0, 1. And, yeah. So we'll talk about the complex case next time. I wanted to zoom ahead here for a second while I got this thing out. Yowzers. Oh, here's a 3x3. Relatively sparse. Like this is uncoupled. That makes the problem not as much trouble. So to make it more interesting, I should have all non-zero numbers so it's completely intertwingled. Coupled. And anyway, long story short, 2, 2, 3 eigenvalues. So you find for the 2 eigenvalue, when you look at these equations, you just get one equation and the others are just the 0 equations. So that leaves you with u and the w coupled and the v is completely free, which means that you got 2 parameters. So you can set like u equal to 1 and v equal to 0. That gives you one vector. You can set v equals to 1 and u equals to 0. That gives you a different vector. You get 2 linearly independent eigenvectors, in this case, attached to eigenvalue 2. So this is what can happen in the third order case. And then with eigenvalue 3, you just get this one, like something along the z-axis, basically. And so there's your general solution. Of course, third order systems are more work. Here's another one where we have eigenvalue 2 repeated again, but this time you only get 2 eigensolutions. So this missing an eigensolution in the repeated case also happens for the third order, not surprising. But the interesting thing about systems, guys, is everything interesting happens for 2x2 systems, pretty much. Like all of the general possibilities are there already at the second order problem. So that is nice because that means I can just test on the second order problem and I don't feel bad about it. It also makes me feel not as much of a monster because I know linear algebra is not a prerequisite for this course, and well, if you did enough homework on this, you'd eventually get up to speed. It bothers me not at all the test on the second order problem in general, and then in the third order problem, I try to throw you a bone if the linear algebra gets a little bit too rough. I was looking for a picture. Where's my picture? Come on, I got pictures in here somewhere. Where'd my picture go? Where's my picture at? Oh, there it is. So obviously at some point or another you're going to ask, what does this all mean geometrically? So like here's a problem, and so what's going on, guys, is that if you look at the solutions, there will be the eigenvector directions. There'll be like, you can see the eigenvector directions, it's this and that, and the solutions just kind of like get drawn into them asymptotically. And anyway, we'll talk more about that later. I should shut up. I think I'm out of time. So thanks, guys. Next time, we'll do the complex case. So.